Okay. This is the last of the 3 assignments I've given you this week. I will be giving you more assignments per week after this, but we're just getting started. I want you to get used to the process. I want you to get the fundamentals down for what we're doing, and you'll start tackling more stuff, probably 6 to 9 topics a week. So this was a very easy one. In fact, this won't take much at all. You'll just zoom right through this. Zoom right through this. We're going to be approximating limits using just looking at graphs. We're not even going to graph these things. You're going to get problems which you're going to take a look at graphs and be able to figure out what the limits are based upon what you see. Okay? A lot of times all you have to do is look at the graph. Well, when I say look at the graphs, we're assuming that that you're going to be able to figure out what the graphing calculator is telling you. If they give you a graph in the book, that's going to be a lot better than using the one on your calculator. Your calculator is a great tool. Don't get me wrong. I love Texas Instruments calculators, except mine, which I'm going to bury by the end of the year. But they're limited by, again, I use the word macro. Macro means large. They are macro graphs and not micrographs, where you get to see the intricacies of these small differences between points, which is grossly important for this topic. So we're going to use graphs. On page 55, problem number 9. So if you open up your book to page 55 and look at problem number 9, you'll see a number of graphs on the left-hand side. Okay? The first one, you'll notice that the graph is a linear situation, and the limit is at x going to 3 for whatever reason. There really isn't a limit there, but if there is one, they're saying it's going to be at 3. And so they put a dot there where x is equal to 3. The fact that there is a point corresponding to it tells you that this is going to have a limit of 1. Okay, but you don't even have to say what the limit is. You just have to say whether there is a limit. And the fact that there is a limit is described by the fact that there is a point on there that you can identify as part of the graph. Number 11, if you take a look at the graph there, before you look at the graph, you look at the equation. This is what is known as a discontinuous graph or a conditional graph. It's more of a conditional graph because discontinuous means it doesn't flow completely, which it kind of doesn't do. But the fact that it says here that when x is equal to, the value of y is 0. That's a condition. Normally it would be undefined based upon what that is saying, but the fact that we have a point for that in a linear situation that is not on there tells us that the limit as x approaches 2 is going to be 0. The value of y when x is equal to 2 is 0. So that means the limit then is going to be 0. Okay? In problem 13, now this is kind of similar to number 11, except when you take a look at 5, 2 things just has red flags waving all over the place. One, if you have x is equal to 5, that means you're going to have 0 for a denominator. That ain't going to happen. And the other thing is they emphasize that they have an absolute value on top, which means all values have to be greater than 5 in order to be positive, 5 or greater than positive, but because of the fact that you cannot use 5 because of the denominator, it's going to have a circle at the end of the bottom line and at the beginning of the top line, which means there is no limit. There is no value that you can get for that, and therefore, because there's no numerical value for y there, there exists no limit whatsoever for f of x. Now, number 16, you have to be looking at what it's asking for there. Again, it's the limit of the sine of pi times x. But they give you the graph, so you don't have to worry about it. You can punch that in your calculator and see what you get. But you're going to get a sine curve wave. But since you're looking particularly at the point x equals 1, there is a point there on the curve at y equals 0, or x equals 1. So that means then, I have this incorrect, it should be 0. So the graph, the meaning of the function then is going to be 0, not 1. We need to fix that. I looked at the x instead of the y. 17 is one of those weird graphs, and this does happen from time to time, in which there is no way of telling what it's basically what they call an oscillation or vacillation, in which the curves are so close together it's almost impossible to determine how far apart they are. And because of the constant oscillation, there is no clear distinct value when x equals 0, so there is no limit for that. So I want you to do 10, 12, 14, 16, and 18 on that page. Determine if there's a limit or not. And if there, it doesn't say you have to tell me what it is, but they are asking why there isn't one if that's the case. So that's all there is for that. I don't think that's going to be too difficult, but let me know if you have issues with it, and we will talk about it. All right. Have fun.